Hello, in this video we're going to talk about AP Chemistry's topic 2.7, VSEPR theory and bond hybridization. And for this video in particular, we're going to focus in on VSEPR theory. I am going to talk more about hybridization in a second video related to this. But for now, we'll focus on VSEPR theory and just briefly mention hybridization. So VSEPR theory is the idea that molecules form their molecular geometries by electron pair repulsion. In other words, when you have pairs of electrons around a central atom, those pairs of electrons repel each other according to Coulombic forces, and therefore they're going to spread out as far as they can in order to minimize repulsion. So with VSEPR theory, you can start predicting what shape molecules will be by looking at how many pairs of electrons are on the central atom. So we're just going to go through the different geometries that can exist and what those molecules look like, and also just some basic physical properties of those structures. So our first molecular geometry we're going to talk about is the linear structure. And in the linear structure, you have a central atom, and bonded to that central atom, you have two atoms on either side. So since the atoms are on opposite sides of one another, that means that the bond angle is 180 degrees between those two bonds. And notice that we don't have any lone pairs on the central atom. So the only pairs of electrons are actually tied up in these bonds themselves. So those electrons are repelling each other, and the farthest they can repel each other is on opposite sides of the molecule. So that's why we end up with 180 degrees between these bonds. So there are always going to be two atoms bonded to the central atom in linear model, and there's going to be zero lone pairs on that central atom, which creates that linear model. So for hybridization, which again I will talk in more detail about later, the hybridization of this model is going to be sp2, sp, sorry. And that's under the valence bond theory that predicts this hybridization. So sp always belongs with linear structures, and we'll talk more about what sp means later on. Second structure we're going to look at is called trigonal planar. And trigonal planar molecules, as the name implies, trigonal meaning that there are three different atoms on the central atom, and planar meaning that it's flat. So we have a central atom, and around the central atom, three atoms are bonded. And notice that there's equal spacing between these atoms. There's no lone pairs on the central atom, and just pairs of electrons in the bonds. So 3 bonds, 0 lone pairs. The farthest that these bonds can get away from each other is 120 degrees. So the bond angle is 120 degrees between these atoms, and the hybridization is sp2. So our next one that we're going to look at is related to trigonal planar, but instead of having 3 bonded atoms, one of the atoms is replaced by a lone pair. And this one's going to be called bent. You still have your central atom, but now when you draw the Lewis dot structure of this substance, there's a lone pair in the place that the other bonded atom would have been. And so on this particular structure, we have 2 bonded atoms and 1 lone pair. This still has around 120 degree bond angle, but it's going to be slightly less because lone pairs are slightly more repulsive than bonded pairs. And so we get a slightly less than 120 degrees, but it's very close to 120. So if you put 120, that would be fine. We still have sp2 hybridization, and these two structures are very much related to each other because they have 3 electron domains. In this case, the domains are 3 bonds. And in this case, we have 2 bonds and 1 lone pair. So those two structures are extremely related to one another. So we're going to leave the trigonal planar types of molecules, and we're going to head to the tetrahedral types of molecules. So our first one is called tetrahedral. Tetra meaning 4. So for the model, we have a central atom, and then there are 4 bonded atoms. Now remember, 3-dimensional structure here, so these are not going to be flat. Here, you're going to have a 3-dimensional structure that looks like a little pyramid with 3 kind of pyramidal on the bottom with 1 on top. And we have 4 bonded atoms in this particular structure. If you look at it, there's no lone pairs on that central atom. And so the bond angles, and this is a really tricky one that's very hard to calculate, but the bond angles here are 109.5 degrees. between these different bonds. The hybridization is sp3, and again, we'll talk about that in a future video. So, tetrahedral, 4 bonded atoms, no lone pairs. Related to this is if you replace one of those atoms with a lone pair, like ammonia, NH3, you end up with what's called trigonal pyramidal. And trigonal pyramidal molecules are just like the tetrahedral, but there's a lone pair replacing one of the bonded atoms. And again, if you look at the structure of ammonia, if you drew the Lewis dot structure, you would see that there's 3 bonded atoms and 1 lone pair. So 3 bonded atoms and 1 lone pair, but still 4 electron domains. Just one of the domains is now a lone pair instead of a bonded pair. So the angle is going to be, again, very close to 109.5, slightly less because the lone pair does a little bit more repelling of the bonds than the 4 bonds would. Still sp3 hybridization because you still have 4 electron domains. So tetrahedral and trigonal pyramidal. The next one that's very similar to this particular structure, still sp3 hybridization, is going to be bent. And if you do not associate water with bent, you need to get on that. Water is bent, so don't forget it. So water has this bent structure, and the reason it's bent is because there are 2 pairs of lone pairs on the bent molecule. Those lone pairs push those bonded pairs downward and create a structure that looks like bent. There's 2 lone pairs and 2 bonded pairs, so 2 and 2, still a total of 4 electron domains. So we're still going to be around 109.5, but slightly less because of the lone pairs, and still sp3 hybridization. So these 3 structures are all extremely related to one another because they all have 4 electron pairs around the central atom. Just some of them are bonded pairs and some of them are lone pairs. So now we are going to go to our next type of structure and next hybridization, and that's when there's 5 pairs of electrons around the central atom. The most basic of this is when you have 5 bonded atoms to the central atom, and this is called trigonal bipyramidal, which I'm just going to abbreviate trigonal bipyramidal, or bipyr, but that's trigonal bipyramidal. Notice that if you have more than 4 pairs of electrons around the central atom, you are going to violate the octet rule. So everything we talk about from here on is going to violate the octet rule. So with trigonal bipyramidal, there's a central atom. There's 1 atom bonded on top, 1 atom bonded on the bottom, 1 atom bonded to the side, and then kind of trigonal planar around the middle. 3 around the middle. So 1 on top, 1 on bottom, 3 around the middle. So there are 5 total bonded atoms to that central atom and no lone pairs. So if you look, there's actually 2 different bond angles here. You have a 90-degree angle between the top atom, top bond, and the side bond, so 90 degrees there. Same with the bottom to the side, 90 degrees. And then you also have the 3 around the middle, which are like trigonal planar, which is 120 degrees. This type of hybridization is called sp3d, because now d orbitals are getting involved in this type of molecule. If you expand the octet, that means electrons are jumping to d orbitals, and that's why the d gets involved in the hybridization. Again, more about that in a later video. Related to trigonal bipyramidal is our seesaw shape, which of course is a fan favorite for names. With seesaw, one of the bonded atoms is replaced by a lone pair. So I'm going to replace this one on the side with the lone pair. So 1 on top, 1 on bottom, and then 2 and a lone pair around the middle. So if you'll notice, you have the seesaw shape. This would be the base of the seesaw. This is where the people would sit. It's just turned sideways in this drawing. So we have 4 bonded atoms and 1 lone pair. So still 5 electron domains around that central atom. And the bond angles are going to be slightly less than 90 degrees and 120 degrees. Still sp3d hybridization because there are 5 electron domains. If we take another atom off and replace it with a lone pair, we are going to have what's called T-shape, another fan favorite on names because that is just not very original. So with T-shape, you have 1 on top to the central atom, 1 on bottom to the central atom, one off to the side on the central atom, and then 2 lone pairs on the central atom. And notice we make a T shape for the molecule. So there's 3 bonded atoms and 2 lone pairs, still 90 degrees approximately and 120 degrees. Actually, sorry, just 90 degrees because those lone pairs take out that 120 degrees. And the hybridization is still sp3d because there are 5 pairs of electrons around the central atom. 3 of them in bonds, 2 of them in lone pairs. By the way, if you haven't noticed yet, look how many letters are in the hybridization name versus how many domains are around the central atom. S, 3 P's, and a D. That's 5 total letters in the hybridization name and 5 total domains around the central atom. That's one way that will help you out with the hybridization name as you're thinking about hybridization versus VSEPR. Okay, so these 3 and 1 more are all sp3d hybridization. Our last one is going to replace this one out to the side with a lone pair, and this one's going to be linear. So we're back to linear again. We have the middle atom, central atom, 1 on top, 1 on bottom, and then 3 lone pairs around the middle. And that is going to be linear. Not very common structure, 180-degree angle, but still sp3d hybridization. So these 4 structures are all extremely related to one another because they always have 5 electron domains around the central atom and have sp3d hybridization. And that brings us around the bend to the home stretch, the sp3d2 hybridization, where there are 6 atoms or 6 electron domains around the central atom. So the first one we're going to talk about is octahedral. With octahedral, there's a central atom. There's 6 atoms bonded to the central atom on this one. So it's kind of like a square, 1 on top, 1 on bottom, 1 on the side, 1 on the side, 1 coming out towards you, and 1 going in away from you. And so this one, all the angles are 90 degrees. And there are 6 atoms bonded to the central atom and no lone pairs. All the angles are 90 degrees, which should be pretty obvious to you on this one. And this one's called sp3d2 hybridization. There are 6 electron domains, and notice there are 6 letters in the name of the hybridization. If we replace one of those atoms with a lone pair, then we get a new structure called square pyramidal. Square pyramidal. In square pyramidal, central atom, lone pair replaces one of them, and then all the other ones still exist where we talked about them in the previous structure. So now there are 5 bonded atoms to the central atom and 1 lone pair. What is that lone pair going to do to all these angles? Well, we've talked about that. It's going to decrease the angle slightly, so slightly less than 90 degrees, but the hybridization is still sp3d2 because there are 6 electron domains around that central atom. So what if we replace another atom with a lone pair? Well, then you get square planar. And with square planar, you have the central atom, lone pair on top, lone pair on bottom, and then 4 atoms around the middle. So for this one, we have 4 atoms bonded to the central atom, 2 lone pairs. All the angles are going to be 90 degrees here because the lone pairs are actually pushing equally on top and bottom of those bonds, and so you're going to have 90 degrees. The hybridization is still sp3d2 hybridization because there's 6 pairs of electrons around the central atom, bonding pairs and lone pairs. Last one. I bet you didn't think we would get there. The last one is if we replace one more of those with a lone pair, we get T-shape once again. And with T-shape, we have the center atom, we have lone pair on top, lone pair on bottom, lone pair on the side, 1 coming out at you, 1 going off to the side, and 1 atom going back into the screen. So you can see we have the T-shape just like earlier, it's just turned sideways here. There are 3 bonded atoms, 3 lone pairs. The angles are going to be slightly less than 90 degrees because now we have an unbalanced number of lone pairs, but still sp3d2 hybridization. So Knowing these structures is really important because if you know their shapes, then you can predict whether the molecule is polar or nonpolar, and being able to predict whether molecules are polar or nonpolar predicts their physical and chemical properties and how they're going to behave with one another. So all four of these are related to each other because they all have 6 electron domains around the central atom. The most important ones you need to know in these structures are definitely the octahedral. You definitely need to know trigonal bipyramidal, because that's another common one that you'll run across a bit. And then you need to know everything smaller than that, because everything else are very common structures that you'll see over and over and over again. So all of these are the most important that you need to know. Again, knowing these shapes and knowing these structures, being able to predict them quickly from Lewis dot structures allows you to predict the chemical and physical properties. So if you need help with these structures, let me know. We'll be using them in future lessons. So I wish you the best of luck. And again, contact me if you need some help.